And our next speaker is another core Ember member, Max Grand from Landing Marine Labs.
Thank you. Good morning, everyone. My name is Max Grand. I'm a chemical oceanographer here at Landing Marine Labs, and I've been studying the cycling of metals in the oceans for the past 20 to 25 years. So naturally, when the fire happened, and Ivano started to share some of his results with us after the fire, and I found out that we were talking about nickel, cobalt, and manganese, I got somewhat excited and curious, and so I decided to apply my expertise to look into the metals within the water at Alcorn Slough. So I'm team water, pretty much, rather than team soil that we had before. So Ivano and Kirsten gave us a very nice introduction, but Ember, we have three compartments pretty much. And the first part was kind of the initial response, what are we dealing with and how much materials have been deposited. And Ivano laid out all the evidence that he acquired to point to the battery in terms of the increases of metals that you saw in Estomage. I want to take that a step further now and think about what happens next. Where do the metals go? Where are they transported? And one obvious candidate is the main channel of the Alcorn Slough, because that is the main conduit of water, with water coming in and coming out and all that stuff. So looking at the water column allows us to start to look into the question, where did things go and what is the magnitude of the export of those metals from the marshes, pretty much. And later on, we'll hear about the biota stuff and the biological exposure work in the next couple of slides. So I was told to have a slide with some simple questions. So here we go. First question we're going to look into today is, did the battery fire leave a detectable signal in Alcorn Slough, in the waters, the main channel of Alcorn Slough? The second one we'll get into is, what can the water column tell us about the fate of those metals following the battery fire and afterwards? And then we'll hit upon another question, how much metals, what is the mass of metals that may have been carried out to Monterey Bay or maybe elsewhere in the slough by the tides? And the last part is very preliminary. We'll get back to that in a second. So the approach here is to look at the main channel of the Alcorn Slough. And why is that? Because it's the main conduit. And when you have, the tide flooding the marshes, the water comes out and will flood through the Alcorn Slough on its way out to the Monterey Bay. So it's going to integrate all the inputs from surrounding marshes, including contaminated marshes and uncontaminated marshes, pretty much. The other issue we had is that, unlike Ivano, we do not have a baseline for metals in Alcorn Slough. No one measured dissolved metals in Alcorn Slough before we did. So we had to think of an approach, because if I show up in September, like some did, and take one sample, I'll be able to get a concentration. But what does that mean? Is it high? Is it low? Is it the fire? I can't tell. So we decided to do a time series. That is, we decided to go back at that sampling site right here every month for a year, either at high tide or at low tide, while collecting a sample every hour from high tide to low tide or low tide to high tide, pretty much. And we focused our efforts on the outgoing tide, because we're looking at export of materials from the marshes into the main channel towards the Monterey Bay, pretty much. So what we did is that we showed up at high tide, for example, got a sample, and did that every hour until the next low tide. And so we started this on February of 2025, finished up in March. We got 11 tidal occupations, 8 hours each. That's about 90 hours at the same spot, right on that star that you see here. So it's a lot of time to think about the Alcorn Slough and breathe, I would say. And we got 9 occupations during ebb tides and 2 occupations during flood times, just to give us a bit more context, like what's coming in from a Monterey Bay, so we can compare things properly, pretty much. Yeah. And before I get going further, I'd like to show a picture from the paper that Ivano published a couple of months ago. So this is nickel as a function of time in the Estomage. You've seen something similar fairly recently. So these are the data before the fire and after the fire. The point I want to make here is that this is when we started sampling the water column. It was hard for us to mobilize quick enough. There is lots of work you need to do before you can actually sample for metals, pretty much. And as you can see here, by that time, the signal in the marshes had already declined by quite a lot. So everything I'm going to say after this slide, it means pretty much that we may have missed part of the signal, because it had already moved along in the marshes before we showed up with our water column experiments. In terms of our methods, here is one of the boats from the Landing Marine Labs that we used to do that work. we use strictly a state-of-the-art technique, I would say, and trace metal clean sampling technique, because in this field, you have to be a little bit crazy and you have to worry about contamination all the time. And you want to minimize that as much as possible. That's why we have all those instruments on the boat to make sure we have clean samples pretty much. And we measure dissolved and particulate metals. So dissolved metals, just filter the seawater through and you collect what comes out. So those are the metals that are dissolved in the water column. And what lays on your filters, that stuff you see right here, is the particulate phase. And we analyze that as well because there is some interesting dynamics between the dissolved and particulate phases in all estuaries. In terms of the analysis, I work with some colleagues at UCSC to extract the metals from the seawater so I could actually analyze them using ICP-MS, so for the dissolved metals. And for the particulate work, we did that in-house, did a digestion, and then run that on the ICP-MS as well. So this is state-of-the-art. These are the techniques that the international trace metal community is using to monitor metals in the oceans, pretty much. So you can't get much better than that, is what I'm trying to say. So here's our data set. We got about 100 dissolved samples and 100 particulate metal samples. And we also got historical data only for particulate metals, unfortunately, from 2019 that I got as part of the class I ran here at Moss Landing in 2019, pretty much. This is a fairly complex plot, but the important thing is that when you sit around in the Alcorn Slough at the same spot for 8 hours, the water is constantly moving, right? And so if you want to compare from March 2026 to February of 2025, you want to make sure that you're comparing the same tidal stage. If not, you're comparing apples with oranges, pretty much. So what that shows you is the sampling coverage across the tides and seasons. So every single symbol you see here is a sample that we collected, and it's color-coded by the month of sampling. And I'm not going to bore you with the angles here, but basically high tide is here, that's when we start, and we go all the way to low tide. So that's an outgoing tide event, pretty much. And low tide to high tide is the bottom of that circle here. So that's when you have Monterey Bay water coming into the estuary, and we sample that as well. As you can see, we got way more samples during the outgoing tide, the ebb tide, by design, because we're looking at export, pretty much. So I told you we don't want to compare apple with oranges. So in the rest of this presentation, or at least for the dissolved metals, we're just going to look at those samples we collected around here, which is right before the low tide and at low tide. And why are we doing this? First of all, because I don't want to bore you with lots of data points. And second of all, because this is when you expect to see the highest signal from the marshes that are draining all that water into the Alcorn Slough main channel and eventually out to the Monterey Bay. So let's now start to look at some dissolved data. So the top panel you see here are dissolved cobalt concentrations as a function of time. So those are all the months that we sampled from February of 2025 all the way to March of 2026. And at the bottom is nickel, same thing pretty much. The concentrations are parts per billion, which means micrograms of metal per liter of seawater. And all the blue symbols are the individual samples and concentrations that we collected. And those boxes, don't worry too much about them. Just follow the line here, which gives you the median, which is roughly the average concentration that we measured during that event, pretty much. And once again, these are all the samples close to low tide. And so what you can see is that the cobalt concentrations were very high, higher in February of 2025 than they were in March 2026. And you see roughly the same thing for nickel as well, even though the decay timescale is a bit longer, I would say. But clearly, we're seeing like a classic example of a pulse contamination that decayed with time, right? So it seems that we're returning towards some sort of a baseline, maybe a natural background, I don't know yet, towards that part of the time series here. And, relative to March of 2026, the concentrations of cobalt were 2 times higher and 3 times higher for nickel in February of 2025. And you may think it's not that much, but you got to think we're talking about micrograms per liter. And for every single ebb tide, we got about 1,000 Olympic swimming pool of water passing through. So if you multiply the volume by the micrograms, then it starts to add up quite quickly, pretty much. So that's a big change, I think, for the Alcorn Slough. So let's put a bit of context onto that, because we're all from the Bay Area, so to speak. So what we can do is compare our data that we have with some data from South Bay, which are a very different estuary here. So we have Alcorn Slough, which we all know, very rural. We don't have a big city around it. and South Bay, which is surrounded by industry, housing, roads, etc., etc. So what I did is that I took all the data I could find from South Bay for nickel and cobalt, took an average, and plotted that on top of the plots I showed you earlier. And this is the dashed line that you see right here. So as you can see, for Elkhorn Slough, we're looking at concentrations, for example, for cobalt that were 10 times higher than the median concentrations you would find in the late 1980s in South Bay, which is a very highly industrialized and polluted estuary. For nickel as well, especially early in the record, we see fairly high data. So clearly there is contamination when you're comparing two things that you shouldn't compare because they are very different, but that's for context, I'm giving you this. Another line of evidence as well that's pointing towards the battery metals, we're talking about cobalt and nickel. Why don't we look at another metal that was potentially not so much involved in the fire, which is copper. So here is the trend for copper over the entire time series. And you see, we don't see that classic decline with time at all. We see some sort of, moving around some sort of a baseline here. So we don't see that trend for a non-battery metal, which points to a battery source. And if you look at the South Bay, it's loaded with copper over there, but it's not in the Elkhorn Slough, and the opposite was true before. To me, that's pretty strong evidence that we are indeed dealing with battery metals being exported from the marshes into the main channel on the Elkhorn Slough. Another line of evidence for these metals is to look at the nickel to cobalt ratio. You're going to hear a lot about that today. So same plot as before, here is time, and here is our nickel to cobalt ratio. The point I want to make is that the nickel to cobalt ratio was very, very different in February 2025 compared to the rest of the time series. And actually it trended towards what's been measured in marshes and also in some of the ghost wives that our enamel pattern partners collected right after the fire as well. So that tells you that there was something going on in the main channel that was very different from other years in terms of the ratio of those two metals in the water column of the Elkhorn Slough. So let's look at the particulate data. You're seeing some very beautiful picture of the stuff that we collected from the Elkhorn Slough. Those are some of our blanks, because in this work, you have to be very careful. And the story is a bit different there. So now we're going to look at the data a bit differently. We're going to take all the samples that I got, so about 104 of them, or maybe 91 on these plots. And we're looking at particulate nickel on the y-axis as a function of particulate cobalt. So once again, that's the solid stuff pretty much. And we're plotting all the points together and fitting a regression line through them. And as you can see, both particulate nickel and particulate cobalt were tightly correlated throughout the entire time series that we've done in the Elkhorn Slough. Once again, those points are color-coded by the month of sampling. So if you are expecting to see, a signal in the particulate phase, you would not be seeing it. You would expect to see some sort of a break in that line. Maybe the early samples would sit around here or here, but not a straight line like this. So it tells you that at least there is no obvious fire signal in the particulate data that we have so far. And we can take that a step further and overlay some of the data that my class collected back in 2019 at Moss Landing Marine Labs. These are those yellow stars that you see here. And as you can see, they plot directly on all the data that we collected after the fire in 2025 and 2026. So there is no apparent shift in the particulate nickel and cobalt composition of the particles suspended in the Elkhorn Slough following the fire. We can also restrict that analysis just for those low tide samples. So that's why you see less symbols here, and the same relationship holds. The slope, that is the nickel to cobalt ratio, did not change at all. And we're still seeing that point from 2019 right on that line as well. So the story, at least from what I can see right now, is in the dissolve phase and not so much in the particulate phase as part of this story. Okay, so now we know that. Let's try to do some math together and try to figure out, how much metals are we talking about? How much metals passed by me or by us as we were sampling throughout that entire time series? And the question here is, are we talking about 1 gram, 10 kilos, 10 tons? This is a back of the envelope calculations with some very crude and preliminary assumptions, but it's still useful to look into that. So to do that, what you can do is take the mean concentrations of the metals that we measure dissolve in the water column during every single occupation. That's what you see with those black symbols here for nickel and for cobalt on the right-hand side here. And you can plot that against the day since the fire ended. So I took that as January 20th, when I think the fire ended pretty much. So day 0 and day 400 is March of 2026 when we finished that time series. So next we can fit this data using what we call the first order exponential decay model. And that's the blue line that you see in both plots right here. And that's quite useful. First of all, just a bit of a disclaimer. We don't have that many data points here, right? So it's a very rough model that I'm doing here. I wish I had more. I don't right now. We'll try to improve that a bit later on. But what's useful is that you can use the model to, for example, predict, what may have been the concentrations of nickel right when the fire had ended in the water column of the Elkhorn Slough. So here it should be about 4 ppb according to that model here. It may not be true. So that's useful because we did not sample before that date pretty much. We can do the same thing for cobalt. And we can also estimate what is the half-life of those metals in the estuary, which is the time it takes to deplete about 50% of the initial inventory of metals initially in the water column. And we can also use this model to estimate what might be our background. What is the background concentration of nickel and cobalt that you should observe if we didn't have a fire, pretty much. That's what this means. So it should be about 1 ppb for nickel and 0.2 ppb for cobalt. So based on that, then we can do more math and use the model to predict what may have been the concentration of dissolved nickel and cobalt for every single peptide from January of 2020 all the way to March of 2026. You got about 800 or 900 of them. And then we can use some relationship that tells us how much water is flowing in the main channel to calculate the cumulative export of metals out maybe into the Monterey Bay or further downstream into the Elkhorn Slough, which is what I've done here. So here you're looking at the cumulative export of metals, nickel and cobalt. Nickel is in blue and cobalt is in orange as a function of time. So of course, we're talking about the excess concentration. So that's the modeled measure concentration minus the background concentration that we got towards March 2026, pretty much. So, and that's most likely fire derived based on what I showed you earlier on. And we can calculate that we got about maybe 500 kilograms of nickel and 150 kilograms of cobalt that must have been exported from January of 2020 all the way down to March of 2026 using that exercise. Warning, very few observations, so the model is very crude. I didn't do any sensitivity analysis. I did that 2 nights ago because I got really excited. There is no uncertainty, and those numbers will be uncertain. It's probably 500 kilograms plus or minus 200 or something around those lines. And I made many assumptions as well that I think are valid, but I need to check on them pretty much. So this is very preliminary. All right. Oh, wow. I went much faster than I thought I did.
Oh.
Okay. So in terms of summary and conclusions, did the battery fire, leave a detectable signal in the Elkhorn Slough? I think the answer is definitely yes, but only so far for the dissolved metals. There may be a signal in the particulate phase, but it's quite subtle, and I need to look at the data a bit more just to see if it's really not there, pretty much. The evidence for that is that we find elevated dissolved nickel and cobalt concentrations right after the fire and for about 3 months. So we see that classic perturbation returning back to a background. We don't see any trend like this for other battery metals. I showed you copper today, but I could show you zinc and you'll see the same thing. And we also have those very unusually low nickel to cobalt ratio for the first month of a time series, which tells you that something very odd was happening in the main channel of the estuary at that time. What happens to those metals? Well, there is little evidence of a particulate signal. And the data may suggest that we're dealing with rapid dissolution of those nanoparticles following that deposition and export in the dissolved phase, so dissolved in the water column, rather than attached to particles. So in estuarine geochemistry, some metals are more sticky than others, and they like to stick to particles. We don't see much evidence of that, which I find quite surprising. That's something I want to look into a bit more later on. So it seems that the nickel and cobalt stage, or once they got flushed into the main channel, that they stayed in the dissolved phase and were exported probably out to Monterey Bay. And finally, were there metals exported out of the estuary? Yes, my initial estimates suggest a substantial dissolved metal amount, but quantifying that export properly is an active area of research. So stay tuned. And that's the reason why I'm not giving the numbers towards the end, because I don't want you guys to remember those. Just tell you that yes, metals were exported pretty much. I'd like to thank all the people that helped me out to do this because it really takes a village. I'm not going to go through the names, but we spent a lot of time at the same spot in the Elkhorn Slough. Sometimes when it was raining a lot and we had to rush back to the Highway 1 bridge to hide from the rain, pretty much. I'd like to thank all my UCSC collaborators, mainly Phoebe Lamb, Alison Lobach, and Brian Brewer, because all the analysis for the dissolve phase were done there, thanks to the state-of-the-art instrumentations they got from the National Science Foundation. So thanks to them. And of course, that work is very expensive. It's about $150 to analyze one sample for dissolved metals, and it takes about one full day from sampling to analysis to get a number on that sample. So thank you to Julie Packard, Nancy Burnett, Louis Steffens, and the Renewable Natural Resources Foundation, which gave us a planning grant, a small grant to carry on with our work and take it to the next level. And thank you all for listening to my French accent today. Thank you.
Now we have plenty of time for questions because apparently I intimidated the speakers in being here.
Assume for a moment that I'm a wonderful little sea slug and I'm in the marsh and I'm down towards the ocean away from where you're taking your test. Is this flowing water over a period of time dangerous to me?
Well, I'm not a sea slug. And I'm not a sea slug specialist, so
I do that for her.
Yeah. The question was, is the metals that were exported, are they dangerous to organisms that would reside in the Monterey Bay, pretty much? And I can't tell you that, pretty much. I do not know. But the concentrations are high, but not really, really high, is what I can say. And remember that the Monterey Bay and the ocean is a big place, and dilution is the solution to pollution, right? So yes.
I guess, could you speak a little bit about like the functional differences or the chemical differences like between dissolved and particulate metals? Like what should we take away from the difference between those two?
Well, it's different phases pretty much. So dissolve is dissolved in the water column, and particulate is attached to particles or on particles themselves, pretty much. I think what you should take away with it is that it depends on who you are in terms of an organism, what matters. So if you are, a filter feeder, maybe like what's stuck to the particles is what matters most, but all organisms will react to the pool of metals that are dissolved or around them in the water column is what I would say, kind of. So, and the key here, we're looking at both those compartments because metals cycle back and forth pretty much. So they would stick to a particle and then the condition would change, redox, for example, and go back in a dissolve phase and back and forth. So they hop around like that in a classic estuary, which Elkhorn Slough is not, by the way. But that's kind of the idea. And that's why we're looking at both phases to get a real mass balance. But most of the metals are in the dissolve phase, which I was quite surprised about, actually. Does that answer your question?
Yeah, thank you.
Do we have a question on Zoom?
We do, yes. We have a question. Is there a reason you did not present manganese data in your talk? Or can you speak to manganese?
Yeah, the reason why I didn't present manganese is that I wanted to keep it simple. I was told keep it simple, first of all. Second of all, manganese doesn't really show that decline with time. And the reason for that is, of course, it was part of a battery materials, but there is also already a lot of manganese in the estuary. And also manganese is kind of a tricky one because it's very particle reactive. It forms oxides on the side of particles that attaches to metals, etc. So I do have the manganese data. I will be discussing the manganese data in my paper, but I did not include that today, mainly because it was a bit too complicated. And also because it doesn't show that fire signal, I think because the background is already quite high in the Elkhorn Slough estuary. But the concentrations we measured of dissolved manganese right after the fire, I think, yeah, from what I remember, I talked to Ivan about that yesterday, were higher than what you expect, what you see in South Bay in San Francisco as well, and then went back down afterwards. So there is clearly some manganese, but the trend is not as clear, is what I'm trying to say. So,
Steve.
Is there any information on the ultimate input of these metals from the batteries themselves, like some materials science or someone has looked at burning a kilo gets 100 grams into the air so that you can actually go back and say, we estimate that 50 tons went in, and now you're seeing 100 kilos is being transported by the water. So you get an estimate of what's the relative contribution from the original source input and how much is still on land somewhere and being, degraded, and how much is being transported by the water into the sanctuary.
Yeah, great question. So the question was, is there any information on, I guess, what happens to the battery particles once they are burned and deposited, pretty much?
How much there was in the battery? Like how many batteries were there?
Oh, yeah, well,
How many kilos of those metals were there? With that kind of a fire, how much gets liberated into the air column versus how much remains behind?
So we can guesstimate what was there based, we know it's a 300 megawatt facility, and we know how many modules were in there. So based on that, we can get a rough estimate, of the mass of metals that were in the facility. We can definitely get that. In terms of what fraction of that mass made it up into the air and got drafted away, I think nobody knows. And that's why it would be useful to set up, monitoring systems around those kind of facilities so you can get that number. Because what we're missing is what was the concentration of nickel and cobalt and manganese in the particles in the air during the fire. That is one thing that you would need. Another aspect of your question, I gave a talk at Sandia in Albuquerque a couple of months ago, with some battery specialists. And those guys, they burn batteries for a living, pretty much, which is kind of fun. And they see what happens. And they collect those kind of particles and those materials, that ash that remains after those kind of fires. And so I have a collaboration with them, and we're going to try to get some of those materials, different chemistries, different batteries. And the next step of that research, which is funded by the RNRF, will look into that. We're going to be doing some incubations to see, okay, you add those particles to water. Does it dissolve completely? How fast does it go? And that's going to be very helpful for the model that I showed today as well. So yeah, does that answer your question?
Yes, thank you.
Awesome.
Another one from Zoom, perhaps. And in fact, some of those battery experts are Zooming in today. So hello, and thank you for registering.
Yeah, we have a question asking why you think copper levels were not elevated despite there being a large presence of copper in battery systems.
Yeah, well, that's a good point. There is some copper in the batteries, but I think the bulk of the mass in batteries is nickel, manganese, and cobalt. That's what you got in the cathode. Of course, there is some wiring and all that stuff, so there will be some copper involved. But that's my answer to that. And maybe if a battery specialist can tell me how much copper there was at the Vistra facility, I'll be interested to know. But my take and my understanding is that, the bulk of the mass is those metals we're talking about today. So,
I don't know if you'd be able to answer this from your research, but is there a way to be able to tell in the water column, with the dissolved metals, where in the water column it's more dissolved? Is it more of it's dissolved near the top of the water, the surface, or is it a little bit lower down or more towards the bottom? Were you able to find that, or be able to find that out?
Yeah, that's a great question. So the question was, where in the water column are the metals? Are they at the surface or at the bottom? So, and it was surface sampling that we did here. So, but the key is that the alkanes too is pretty well mixed. So, the currents, if you hang out over there, are really swift pretty much. So the assumption we're making, which I think is valid because it's been documented before, is that there is no real difference between the top and the bottom. Or maybe if you go right at the bottom next to the sediments, you'll see some sort of a gradient. But the water mass or the water column should be pretty well mixed. So if I measure at the surface, at the bottom, or at the middle, I should get roughly the same value.
Jacob?
Just based on that, would you expect the sediment in the main channel to be different than the sediment in the marsh or in the side channel areas?
Yeah, it's definitely different. Mainly because it's the main channel. There is lots of turbulence. Water is flowing really fast. So what you're gonna find at the bottom of the sediment are the coarser fraction. The fine stuff is gonna move away pretty much. So that's one difference in terms of size. Then one thing I was looking for, as part of our experiments, and I need to look into that a bit more, is at low tide, you get lots of resuspension of those sediments. The whole slough gets very turbid. So do we see a pulse of metals that look like battery metals during that time is something I'm looking for. I haven't seen anything like that so far, but it may be there because it's possible that some of the metals got deposited at the bottom of the main channel, possible, and that stuff gets resuspended, and every single low tide you see a signal that I'm trying to look for. But so far I haven't seen that. So.
Michael?
Yes, you have two fractions, you had a dissolved fraction and a particulate fraction. Would the particulate fraction also include, I would assume it would, the diatoms and other biological organisms? So that would be analyzed and that would be representative of what they accumulated.
So, yeah, I mean, basically so the idea, the question was like, does the particulate fraction represent, the organisms that are in the water column as well? And it's, we digest it all pretty much. So you can't tell from what we have what's actually in a diatom, but you can do some calculations using the phosphorus content of the particles to figure out what's from biology and what's lithogenic pretty much. So we can compare those two phases. I can tell you like, yeah, that fraction of the signal is from, rocks or ground up rocks, and that fraction is from the biology. But I can't tell you specifically that the concentration of nickel in a diatom was XX micrograms per liter or micrograms per gram pretty much. So does that answer?
Yeah, that's good because that was your conclusion then that it was biologically linked or attached, or was it the particles were non?
Well, I think it's mostly like a geochemical question. It depends on the size of a particle, the charge of a particle, the salinity around that particle is, so it's not that the biology is taking up the metals, that the biological organism on the particle are taking up the metals pretty much. It's a passive process, the absorption we might be talking about here. I'm not sure I'm following, we can talk about later if you want. Shut up. Yeah.
Let's take a question from Zoom.
Yeah, just one more, following up, I guess, with what Jacob was asking about, Renee online asked, do you think that entrained metal particles could have been deposited in channels due to higher densities?
Do I think that entrained metal so which channel is not quite clear? Is it the main channel or the?
Yeah, does that mean in the smaller creeks instead of the main channel, or?
That's what I
think that's what yeah, it's possible. And that's the next phase of research as well, is to move away a little bit from the main channel and look at those, tidal channels and see if we pick up a signal there as they're draining pretty much. So I hope I am answering the question here. And one thing I'd like to say as well, for the particulate signal we got, I say there is nothing, but it's also possible that most of the particulate signal was before we started sampling. It's actually quite likely that this is when you would see that as well. And also the last thing I would like to say is that we need to continue that monitoring, because I'm assuming that the data I got in March 2026 are the natural background. I don't know. Maybe it's going to keep declining with time, and I would change my calculation quite substantially as well. So.
Well, thank you, Max, for presentation and questions.